Every transistor on every chip you have ever touched was born the same way. A machine fired a beam of charged atoms into a crystal of pure silicon, one controlled burst at a time. Without that step, the silicon stays inert, just refined sand. The machine that does it is called an ion implanter, and the company whose name appears on most of the world's best ones is American. Except that on a growing number of Chinese fab floors, it isn't anymore. Before you call this incremental, a niche tool, a lagging metric, stay with it for a moment, because the implanter is not peripheral. It is the step that makes the switch. Every chip in your phone, your car's engine controller, the power converter in your laptop went through this process. No implant, no transistor. No transistor, no logic. The machine that performs this step determines who can manufacture semiconductors without asking permission from anyone. Control over who builds this machine, at what precision, at what scale, quietly determines the shape of the entire semiconductor supply chain. By the time you finish here, you will understand exactly how ion implantation works, where China's domestic industry has genuinely taken ground, and where the physics still draws the line. Because this isn't really a story about one tool on one fab floor. It's about a floor China is raising and a ceiling incumbents keep moving, and whether those two surfaces will ever meet. One more thing worth planting now. The implanter doesn't just fire, it steers. Something inside the machine does the aiming, and that something turns out to be where the real choke point lives. We will get there. To understand what China has actually built, you first need to understand what the implanter does, and why getting it wrong means no chip at all. Think of a silicon wafer as a sheet of glass you want to turn into a mirror in very specific places only. You cannot paint it. You have to fire silver atoms into the glass itself at exactly the right depth. Too shallow, and they sit on the surface and wash off. Too deep, and they are invisible to the circuit above. The ion implanter is the gun. The trick is the aim. The actual process works like this. Dopant atoms, boron for one type of transistor region, phosphorus or arsenic for another, are ionized, meaning an electron is stripped away so they carry a charge and can be accelerated. A high-voltage column drives them to the target energy, and that energy is what determines how deep into the silicon crystal they will travel. The dose, how many atoms land per square centimeter, is controlled by how long you run the beam. Get the energy wrong, and you have implanted too shallow or too deep. Get the dose wrong, and the transistor's electrical threshold shifts. Either way, the device leaks current when it should be off, or fails to switch at all. The machine must then repeat this, wafer after wafer, with results that stay inside a very tight band. Drift outside that band, and your yield collapses. Some people ask whether you could simply heat the silicon and let dopants diffuse in from the surface. The older method, thermal diffusion, which was standard for decades. The answer is that thermal diffusion spreads atoms in all directions simultaneously, which was acceptable when transistors were large enough that a little blur didn't matter. Modern transistor geometries are small enough that blur destroys function entirely. Implantation replaced diffusion because it gives you directional control. You choose the angle, the depth, the dose. At any advanced node today, there is no substitute. So now you understand what the machine has to do. The question is, who can build one that does it well enough, and for what? Chinese equipment makers have developed ion implanters that are running inside Chinese fabs at mature process nodes. Mature node here means process generations at roughly 28 nanometers and above. The transistor sizes that go into automotive chips, industrial sensors, power management circuits, and the analog circuitry inside almost every consumer device. This is not a small or marginal market. Mature node chips represent the majority of global chip unit volume by a wide margin. Every electric vehicle on the road today contains hundreds of them. Every factory robot, every home power inverter, every industrial sensor array. The reported progress of Chinese domestic implanter makers in this space, while specific production volumes and named fab customers remain unconfirmed in independent public records, is consistent with government industrial policy documents, industry reporting, and the observable pattern of Chinese equipment investment over the past decade. Think of mature nodes the way you'd think of a highway network versus a Formula One track. Formula One gets the headlines, but the highway carries the actual cargo, the chips that run your car's brakes, your home's power inverter, the sensor in a factory arm. China is now paving more of that highway with domestic equipment. And the strategic value of that is not only defensive. A country that can supply its own ion implanters for mature node production can also supply other countries' fabs in Southeast Asia, the Middle East, and developing markets that are building semiconductor capacity for the first time. It becomes an exporter of the equipment layer, not just of the chips themselves. This mirrors what happened in solar panels and in electric vehicles. China captured the manufacturing equipment layer and used it to reshape the downstream product market. The implanter story is the same dynamic, earlier in its arc. Meanwhile, export controls from the United States, which increasingly target semiconductor equipment specifically, are partly designed to prevent exactly this floor raising from reaching the ceiling. The controls are themselves a map of where the gap matters most. If you're wondering why mature node capability doesn't get the same coverage as the leading edge race, the answer is that the chip conversation is almost entirely captured by the smallest nodes. 3 nanometer, 2 nanometer, the next announcement from TSMC. Mature nodes don't generate that kind of headline, but they generate the revenue, the unit volume, and increasingly the strategic independence for whoever can supply them. Second place in a market that is orders of magnitude larger by unit count is not a consolation prize. Now the ceiling. Where does it sit, and who keeps it there? An ion implanter is not one machine. It is a stack of subsystems. The ion source generates the ions. The beamline, a sequence of magnets, focusing lenses and accelerating electrodes, selects the ion species, sets their energy, shapes and collimates the beam, and scans it uniformly across the wafer surface. The wafer handler positions the wafer and tilts it for angled implants because some doping steps require the beam to enter the silicon at a precise off-axis angle. Each of these subsystems carries its own precision requirement, and they all have to work together. Some of these components, the wafer handler, portions of the mechanical structure, can be manufactured with general-purpose precision engineering. Others, particularly the beam steering magnets and the ion source at high energies, require materials and control electronics that have historically come from a narrow supplier base built up over decades. Based on available reporting and the pattern of what export controls target, China has made meaningful progress on the more accessible subsystems. The most demanding beam control components, those required for the highest energy, most uniform implants at the tightest tolerances, remain an area where domestic capability is either unverified or still partially dependent on foreign supply. Subsystem-level sourcing data for Chinese domestic implanters is not publicly confirmed in granular detail, so the honest framing is, progress is real and uneven, with the hardest physics still at the frontier. Think of the implanter as a precision rifle. China can manufacture the stock, the trigger group, even the barrel. But the rifling inside the barrel, the precision-cut spiral grooves that stabilize the projectile and determine whether you hit the target. That's the part where tolerances compound. At mature nodes, the tolerances on that rifling are forgiving enough that domestic solutions work. At the leading edge, they are not. And this is where the "just iterate" objection comes in. If China can build the whole system at mature nodes, why not simply push the engineering toward the harder specs? Iteration is happening. The investment flowing into Chinese equipment companies is real and sustained. But high-energy beam control involves precision that compounds across multiple subsystems simultaneously. Getting the magnet right is necessary, but not sufficient. You also need the control electronics, the ion source chemistry, and the vacuum systems to all perform at the same level at the same time. Each layer of the stack has to deliver. That's why incumbents with decades of integrated development hold a lead that does not dissolve in 1 or 2 product generations. Applied Materials is the world's largest semiconductor equipment company by revenue. Its Varian implant product line, absorbed when applied, acquired Varian Semiconductor in 2011 for approximately $4.9 billion, as reported at the time, represents decades of accumulated beam control engineering that was built up before most of China's current equipment companies existed. At leading-edge nodes below 10 nanometers into 7, 5, and 3 nanometer territory, the implant steps multiply in both number and complexity. Halo implants, extension implants, threshold voltage tuning implants, each requiring beam energies and angular precision that push the physics harder than any previous generation. The dose uniformity required across a 300 mm wafer, the standard size for advanced fabs, is measured in fractions of a percent. Exact specifications at the leading edge are not publicly disclosed, but the requirement is understood across the industry to be among the most demanding in all of semiconductor equipment. What is established by the public record? No Chinese domestic implanter has been independently confirmed in volume production at these advanced nodes. And the export control rules from the United States Commerce Department specifically restrict the export to China of high-end implant tools, which is itself a form of evidence. Governments do not impose costly controls on tools that don't matter. The controls mark the gap. The crosshairs on a rifle scope can be machined in most precision workshops. The internal reticle, the etched glass that stays stable across temperature swings, vibration, and years of continuous use, is made by very few companies in the world. Applied Materials' implant position is the reticle problem. The visible machine is one thing. The accumulated precision engineering inside it is another category entirely. One more objection worth addressing. Couldn't China acquire older machines on the secondary market and use them to close the gap? Secondary market machines exist and have been used, but a 10-year-old implanter built for a previous node generation cannot perform leading-edge implants any more than a decade-old navigation system can locate you with centimeter precision. The physics requirement moves forward with each new node. And reverse engineering a system whose performance depends on the interaction of a dozen co-developed subsystems is not a problem that resolves in one product cycle. It hasn't yet, by any confirmed public account. Here is my honest read. 2 extreme interpretations of this story exist, and both are wrong. The triumphalist read, "China has solved ion implantation, chip sovereignty is within reach," is not what the evidence shows. The dismissive read, "These domestic implanters are irrelevant, a vanity project, nothing to watch," ignores the scale of the mature node market and the compounding nature of equipment knowledge. What the evidence actually shows is a 2-speed contest. One speed at mature nodes, where Chinese domestic implanters are a genuine and growing part of global supply. One speed at the leading edge, where the physics still draws a line that investment alone cannot immediately erase. The floor China has raised is real. A meaningful share of global semiconductor manufacturing, by unit volume, by economic value, can now proceed with domestic Chinese implanters without asking an American company for permission. That is a structural shift in the supply chain, even if it is not the headline shift. The ceiling is also real. The beam precision required for advanced logic fabrication still belongs to incumbents who keep moving that ceiling forward with every new node. The strategically important question is not which side wins. It is which constraint binds first when this one partially resolves. Because the implanter is one layer in a much deeper stack. That's what I want you to sit with. Is the floor. China is raising enough, on its own terms, to reshape the supply chain, even if the ceiling never comes down? Or does the ceiling matter more because the leading edge is where the most consequential chips will always be made? I want your honest read in the comments. Which surface matters more in the next decade, and why? Because I think there are two genuinely defensible answers, and the right one depends on which chips you believe will actually decide the outcome. If you want to keep following this contest layer by layer, tool by tool, subscribe. The next choke point in the stack is already in motion, and it is not the one anyone is talking about yet. Every transistor you have ever used was born from a beam of charged atoms fired into sand. The machine that fires that beam, and the question of who builds the version that aims it best, turns out to be one of the quietest and most consequential contests happening right now. Now you know exactly where it stands.